So, first of all, thanks for being here. This talk is about CI/CD tools and the workflows for HPC systems and software projects. It's intended to be beginner friendly, and I will explain most of the concepts with an example of our own software. So, first of all, who am I? My name is Michael. I'm a student in research software development at FAU at the chair of LSS. I'm also responsible of the CI/CD maintenance, so I'm one of the persons. And at the chair, I would say, have four software topics, two simulation frameworks, waLBerla and HiTech. Then we have code generators, which is Exa stencils, and Pi stencils and LBMPy. So first of all, the usual introduction. What is CI/CD? So the idea about this, or CX, it's usually called nowadays and in the context of HPC, the idea is to improve the development process for basically everyone and allow different developers to work together to improve the software. You're usually differentiating between three types, which is CI, CD, and CB. CI means the continuous integration, so the automatic build and test of software changes to ensure correctness for different architectures, systems, build options. The deployment is sometimes also called delivery. I will just call it deployment for now on, even though some people might argue it's more of a delivery. And there the idea is to produce and ship build-ready environments or the software on the target system so that it can be used by others and yourself. So it's to ensure software availability. And especially in HPC, something that is also really important is the performance. And here CB is there to have performance regression, so to hopefully automatically measure and track performance over time, and the same for scaling behavior. Most of the talk will focus on CI. And the CI or concepts from CI I want to introduce with the help of our simulation software, waLBerla. So waLBerla is a massively parallel, so HPC software framework for multiphysics applications. We focus mainly on the CFD domain, so computational fluid dynamics, and waLBerla is mainly used for the lattice-Boltzmann method. There are also other physical components like particle dynamics, phase fields, free surfaces, and temperature that can be coupled with the simulations, but the main focus is still on lattice-Boltzmann. It is a C++ framework, and it runs on most of the state-of-the-art supercomputers, for example, LUMI, SuperMOOC, many more. And you can use it for CPUs and GPUs. So it runs on both kind of architectures. This is accomplished by the use of code generation. With this, we improve the performance and we also make sure to have our code portable, for example, for GPUs. Yeah, but the talk is not about the code generation part. This is really mainly about the core framework or the framework waLBerla itself and its CI. So to have a CI, the first thing that you should consider is to host your code base, usually with a revision server. The most known is Git. For Git, you also have different flavors of servers that provide Git. We use GitLab because it's easy there to host your own server, and we host it ourselves. And GitLab has some cool features that basically allow to develop your CI infrastructure without some external help. So here you don't really need the HPC tools yet, I would say. GitHub can do something similar. So I assume that everything that I will introduce here will also be possible with GitHub, but in a different flavor. I will focus on GitLab from now on because this is what we are using. So with GitLab, you have something that is called the GitLab CI. And the GitLab CI is a pipeline orchestrator where you write YAML files. So one YAML file, for example, that describe a pipeline. And this pipeline schedules then jobs. So on the right, you can see part of our pipeline, which is one job, a test to be specific, of our CI pipeline. There you define in the YAML way different stages, what it should do. You have the possibility to store and create artifacts. You have pipeline variables for an environment. You can use tags and so on and so forth. And the nice thing is also that GitLab has something that's called GitLab Runner. And this is a service that allows you to queue jobs on existing architectures. So here, for example, at our chair, we have different workstations and compute units for Linux, for Mac OS. For GPUs, we only have NVIDIA GPUs on some of our Linux systems. And the Mac OS ones are ARM, and the Linux ones are x86, and they are of different versions. Yeah, so and with the tags, the runner pick jobs that are scheduled to be queued by the GitLab CI and then be executed. So this is like a really course overview how this works. Now I will go into our CI. Sorry that the slides skip. They continue for themselves. And in our pipeline, the ideas or what our CI does is every time somebody pushes a code change, we want to validate that the code change still results in a valuable framework, a still valuable output. Here we divide our CI into three pipelines, so to say. We have the branch pipeline. This is the one that is really always executed if somebody pushes something. It is there to have really immediate or almost immediate validation for your code change. And the test space is a bit smaller to save resources. Otherwise, it would take too long to get feedback and we would waste too much compute time and energy. This is really for every feature branch. Then we have a merge request pipeline. There, for every branch where we have an open merge request that is not a draft, we test a bit more thoroughly. So we have this stage called test matrix, where we have an intensive space of tests that we execute. You can think of it as a acceptance test. So only if this test passes, it is accepted to be merged in our main branch. And if something appears on the main branch, so it is pushed there, it triggers, so to say, our regression pipeline or the stable pipeline. There not only is the large test space executed, but also our documentation is updated to the GitLab pages. So this is a service provided by GitLab where you can publish your own website, so to say. So our documentation is built and is published there when something is pushed on this pipeline. And we also do performance regression tests there. So the pipeline exists. So all of them have 6 stages, but dependent on which pipeline level, so to say, you are, not every stage is executed. This will become clearer when I go through the stages step by step. First of all, um, we have the CI stage, so the test suite stage, I mean. And here, as I said, the idea is to have immediate feedback for your code changes. Here you see, for example, on the right, some jobs or some pushes that triggered the pipeline or different pipelines. Most of them were working. One of them failed. And here in the CI, you can really see what was the case. So here in the second stage, the Clang tidy process failed. So with this, you can view this. Our test framework, or the smaller tests, usually have three major tests, which consists of tests for free compilers, for GCC, Clang, and ICX from Intel, because these are the ones that we most commonly use. And we vary some parameters like with CUDA, with MPI, without MPI, with OpenMP, with vectorization, and so on. And when you click then here on these CI stages, what works and not, you get also feedback directly in the browser, so it's easy to find your problems and whatnot. So here, for example, where the test suite passed, you can see that 100% of our tests passed, and you also get a summary with the timing, so how long the tests took. Similar to the failed tests, so in the first stage with the test suite, it can either fail during the build process. Here, in some commit, some part of the code generation interface could not build. There you can see what exactly could not be built. You can look at the artifacts then. You can build it locally yourself. And the same is also when the tests then fail. So here everything could be built, but one of the tests failed. Here also it helps to find the reason for this. We execute our tests or everything in the pipeline by making use of CMake presets. So to build our framework, we use CMake, and this has the really nice feature of presets. And we go even further and define something like fragments. I go into this in a bit more detail because I think not everybody is using this for their CI or for their entire workflow. And I think this is something really nice and helpful. So when you build your framework, you would usually do something either when you do it locally with something like ccmake, or you pass like all the cache variables with sometimes a really long list. And this is not so nice for reproducibility, and it's also not so nice to look at. We use something called presets, and with the presets, here I gave you a snippet of the CI test, the Clang one, for example, and the execution that we have. You can see we just use CMake. We say do a workflow and take a preset. And the preset we define here in this job variables. So we define the variable CMake preset name, and we choose the CI branch test preset. And here you can see what the CI branch test preset looks like. So here you would usually have all the variables that you would also pass here with the W flag. It could also be a longer list, but it's still nicer for reproducibility to see what you did when you have it in this preset kind of manners. But we even get a step further and not only use presets, but we also define something that we call fragments. And fragments are just also presets, but that you can inherit. And we use these fragments to specify isolated tasks. So here, for example, if somebody wants to enable CUDA for our framework, then they only inherit the CUDA fragment. The CUDA fragment here, for example, is defined like this. So also a preset. And here you have the Ccache variables. Usually this would be then here in the preset itself. And we have an own build option that's called build with CUDA. And then you have to specify also the CUDA architecture that is being used. And this is the thing that for me is really like magic. I'm really always excited about this. We define this in the preset and we just say when you use CUDA, the architecture has to be defined. And this can be done during the execution. So we define this environment variable, waLBerla CI CUDA architectures, and then I can reuse these fragments in this preset all the time and just specify my architecture for the architecture that I'm using here. So it's working well together. This is really cool. And we use this to enable libraries, for example, OpenMesh, Metis, Petsy. We can change the build type from release, debug. We can use different build tools. We can enable Python, MPI, GPU, and so many more. So these are just some examples of fragments that we defined, which allows us to define the presets in a really concise way to not have code duplications. And this also makes our pipeline really clean. And this is not only working for the CI, this is for the entire workflow. Okay, now I spent some time here. Sorry for this. I think this is something cool that not everybody might know and is really helpful. Therefore, I wanted to spend some time with this. Let's continue with defining the stages of our CI pipeline. One of the stages is code quality. This is just some static analysis tests. For code quality for C++, we use Clang Tidy for linting. We also start Clang Tidy, or we manage this by resets with CMake. And we store the output as an artifact for some time. We also have some Python codes, and there we use Python linters. I don't go into much detail here. Same with the documentation. As I said, we host our documentation on GitLab. But what I want to emphasize here, what I would say is cool about our workflow is that we combine Doxygen with Markdown. And this is something that I really like because most documentations, especially the Doxygen ones, also our old documentation, they're not really nice to read. And I think it's hard to find something there. But here we define readmes as we do with the CMake list txt files for the different hierarchy levels. And these readmes also represent then the structure of our documentation. And you have like the encode documentation from the README that can directly be translated to a web page documentation. So here's some description of the structure. Of course, it supports LaTeX, but it also, for example, uses Doxygen to include code snippets. Here in this preamble section, we include some code snippet from this application where I made a screenshot from the README. And you can see here in the web application, you have the code section with some annotations that you would probably do anyway in your code when you're using Doxygen. And this is really nice. And the documentation stage we do not only when we deploy, but we do this really every time because I would argue that for a good CX system, a good framework, documentation is as important as everything else. So changes in the code should usually involve changes in the documentation, or at least new features. And then you should extend them and should make sure that the documentation can be built. Therefore, we include this in the branch section, and it's also not too expensive. Now we come to the less common part, I would say, of this presentation with the more specific features. Starting with our test metrics. As I said, this is now more in-depth testing for acceptance. And here's a snippet of the test metrics YAML file. So this is, you could say, an own entire pipeline itself. And you can see we have different tests. So we have various combinations, sometimes with MPI on a Mac. Then we have hybrid MPI, OpenMP. Sometimes we have CUDA, sometimes we have not. So we need different versions, and we need different tests. And these are predefined with presets that all use the fragments that we define. And these files we don't write ourselves and maintenance, but we make something that we do really that we likely do, which is using code generation. So we have just a Python file that generates us this pipeline YAML script. In this Python file, what is important is that we specify like what tests we want to have. Here, for example, we have one test that has the fragment for hybrid and for CUDA and so on. And we define all the compilers that we want to test for. To generate a metrics for tests. And for this, we have an own CI stage where just this, you could say this pipeline file, this YAML file is generated depending on what we specify in our generator. And this is then stored as a fragment or pushed as a fragment. An important side note here is that this is not to be confused with the GitLab metrics expressions. So GitLab and also GitHub exports things or supports that you build a metrics out of your test. That means in our case, it would be compilers and build options, and then it creates a test metrics for everything. But this is like a full metrics. But we don't want to test every combination. Some are redundant, some we don't want to test because it makes no sense. And therefore, it's less a test metrics, or you could say it's a sparse metrics, what we do, not a dense metrics. Yeah, so much about this. Yeah, with this generation. So how exactly we generate is not too important, I would say. But what is also a nice feature that we use in our test metrics is the feature to use downstream pipelines. As I said, our test metrics is an own pipeline, so an own CI pipeline itself, that we on demand, so dynamically create when we want it. So in theory, we could also get information from previous tests to go into more depth with other tests if you want. So you can be really creative with this because this downstream pipeline feature from GitLab allows you to dynamically adjust what your pipeline does. So it's, you could say you spawn children pipelines, which we do here. So we have a second job that's called trigger. And this job uses the needs statement to be dependent of the generation. So this will only be queued when the test was successfully generated. Then it takes the artifact that was stored to run the job for the pipeline as a downstream pipeline. This can be done with the command for trigger. This, on top of that, you can dynamically adjust what the pipeline does. It is also nicer to have this. So this is not necessarily a downstream pipeline feature, but from Git that you have this like in this ordered way. But if you have multiple pipelines, it is nice to separate them to understand this. For example, if you don't want to generate the pipeline scripts as we do, you could write like 20 different more intense pipelines and decide if you run them or not, depending on the previous tests. So be more in depth with only GCC, for example. This is also possible. And why I mention this here now in depth is because you can not only trigger pipelines from the same repository called the children pipeline, but you can also trigger pipelines from external repositories. And this is important to know to understand how our benchmarking stage works. So we have a continuous benchmarking pipeline, but only for single node. And why this is because we run our performance benchmarks on the local test cluster from NHR here. Usually running jobs on a cluster from a CI is really hard to set up. There are so many like barriers, two-factor authentication, maybe proxy jumps, VPN to just get to the cluster. But here, the smart or nice thing is that our CI pipeline is hosted not on our server, but it is hosted on the Git server from NHR, so from the one that provide the test cluster. This pipeline can still be triggered from our CI. So we trigger a pipeline on a different server. And why we do this on a different server, it's not just because we can, because the NHR Git repository provides the nodes or its test cluster, you could say, as Git runners. So they have a runner swarm with their different nodes, and they have different GPU architectures, different CPU architectures. It's, as it said, it's a test cluster, so they want to test how is different hardware, how good is it, and therefore they have a lot of hardware. But it's only one node per hardware, so every node is different. So we don't do multi-node runs or tests or benchmarks with this because this is not what our framework is intended to. It's not intended to run on heterogeneous architectures. It's intended to run with accelerators, but not on heterogeneous CPU architectures, for example. And we also don't do scaling tests because this would be also weird for these kinds of architectures. Therefore, it is not possible for us to do like scaling or multi-node benchmarking, but other HPC centers provide these Git runners as well. So it's also possible to do this with other centers. Maybe they can. You can look this up. If you want to have more information about this, this was developed by my colleague Christoph Alt. He also wrote a paper about this. I included the paper here. Okay, now I see that I'm a bit behind, so I will go less into detail from now on. Another thing that you need to run a CI is to have like an environment. So what I wrote here is that we want to validate our code changes, not our environment changes. So we want to have a reproducible CI with the same environment. And we also have different runners, and we want to have the same environment on every runner. Therefore, we use containers since they allow all of this. And GitLab supports something that's called GitLab Container Registry, which you can think of as a Docker hub that is directly in Git. So it's from itself. And there we create images where we run our tests in. Here I have a screenshot from, for example, our Clang images that are in our registry or in our stack. It's also often called. It's an own repository, mainly for two reasons. One is that these images are not only used by waLBerla, so for other softwares as well. So we wanted at one spot. Also, we create the containers directly from a CI to not be forced to do this by hand as a user because this is error prone. And like the developers of applications would be really confused if they have to have errors with some CI, with some containers in a CI. So we exclude this for clarity. Now we come to one of the tools that is really nice to know and to have, and you're probably here for this, which is Spec, because we use Spec to create our environments or our containers. First of all, Spec allows to manage these containers, so you can use Spec and don't need to do on top of this like Docker commands, but you can also push and pull and everything the containers from the stack. We can install our dependencies. We can define really specific dependencies and install them with this. And we define our environments in a reproducible way, and Spec can create like these containers from an environment description. Here, important side note, we create our dependencies with Spec, not the framework itself yet. The CI images are created in 3 steps. We have a base image. This is still Docker, where we get a container, an environment where Spec is running. And we always take a base container from the GPU vendor, because then we have like the proper GPU libraries already there. And then we install every dependency in one step that we have. So every compiler that we want, every library that we want, and we push them to the stack as a build cache. I will come to build caches in a bit. And the last thing, the last step is that we create environments. So we generate them to install the environment directly from Spec. The generation is kept really easy. So you have to define a environment file in the YAML format anyway when you want to use Spec environments. And as we are using Ginger templates, we can include a macro for the changes that we want here, for example, for the compilers. And then we have a generation script that is just where we define all the compilers that we want. And it replaces the macro with the entry from the compiler here and creates folders with this environment structure that we can loop and push then also to the build cache. So we extend the base Docker container with the with the environment where then the CI is run in. Okay, now why I was emphasizing this build cache all the time. The build cache is a feature from Spec that is really convenient because it accelerates the installation of Spec binaries. So when I say we build every dependency all the time, we not actually do this. We just tell Spec, look if the dependency exists. Because when you push a binary, and that is installed with Spec, Spec knows exactly where it is. And we add the mirror of our container registry to Spec. So before installing, Spec will look in all its mirrors to see if an appropriate version of the software that I want to install with Spec install is already existing. And if it is, it will pull the binary instead. So it doesn't have to be rebuilt. We usually only rebuild once in a while, or we rebuild new dependencies that come the way. Yeah, we share the containers of the images and the build cache in the same registry. And just like for your information, there are also public Spec stacks You can look at the cache spec.io website to find some of them. Here I have an example for Petsy. So it's a pre-built Petsy version, for example. Okay, this is about our CI. Now about the deployment. Our way of deploying waLBerla is by deploying our source code. So once in a while, we manually click the release button in Git, which gives us a new version for our software and creates like the tarballs and everything. This we then take to also manually update our Zenodo entry to have a DOI and then a new DOI for our software. This is also something, if you are not already doing this, you should do, because this is now really common that you publish software. So you should have a DOI when you have a publication, so you should really specify what version of the software you're using with a published one. Um, with our CI pipeline, you could also say that our main repository is always also stable, or it is stable. So our main is like a rolling release, but this is never somewhere published. This is just, you can always clone the newest version there and it will work. And due to requirements from EU projects and so, we also create mirrors from our repositories, and this is done automatically. But yeah, arguing about this. Now, I said that deploying in the beginning means making software available, or the executions available at the target system. So you would expect to publish a binary somewhere, or at least a container. But just deploying a container somewhere is usually not working, or not the best way to go. So you can use MPI and things on at least Singularity containers, maybe also Docker by now. But in my experience, it's really hard to set up and it's not always working, and you still need an own container for everything, for every system that you want. Web developers usually just publish the binaries that come out from the as artifact from their CI. But for HPC codes, this is definitely not possible. So one of the older professors at the chair that I'm working on always used to say, or says, that now that hardware always, or resources always become more powerful, it gets even more important to focus on efficient software solutions and efficient codes. Because if you run a really slow and bad performing code on a very good hardware, you're wasting so much energy and potential. So this hardware is really meant to be for good codes. And this doesn't mean that the code is badly written, but that the binary is just not good for the target. So in HPC, I would say you usually want to build directly on the target system. So maybe I'm wrong, but I would say there is no way around building directly on the target system. To do this, we initialized something that's called Research Data Management Repository. This is our first initial attempt for continuous deployment, and especially with a fair continuous deployment. And there we have different repositories in this group. One for scripts. Those are build and run scripts, so things that you would need for the deployment. Then we collect also performance data to have an overview of our performance regression. And we collect also like guidebooks, so good to knows and just information about the cluster to share with everybody and for newer generations. When we have, with especially the first repository here, the build scripts and the run scripts on a cluster, it is still not continuous. So at least not yet. You still have to execute it by hand. There are some attempts, especially from the EU and things like Castiel, to make like really a continuous deployment possible, but I would say we are not there yet. So this is still in development. When I'm talking about EU projects, since Seek is also an EU project, I want to give you an overview over our CI in the EuroHPC landscape. Um, and everything that I told you so far is this part here. So our CI and our CB is completely local and not really integrated into the landscape, other than we needed to have a good software. And our research data management is the first attempt to deploy this onto our target EuroHPC clusters. They are also binary, pre-built binary servers, like for example, these public spec build caches, where we could include our software also. Some of them need like an hook in the on the cluster itself to be used. And if the software is on the cluster, the user still has to execute this. From the EU projects, there are also things like external user interfaces that might trigger jobs like CB on the cluster from an external source. But just to say as an output or to help users that are not known to HPC execute the software there. This is not really part of the usual CX, but I wanted to include this since I think it's interesting to also know that for having really automatization, I would say that you need like this external interface to start jobs and abstract them. Okay, now we are almost at the 45-minute mark. But now we come to the packages. I will go, or to the tools. I will go a step back. So what I now want to focus on is here where we have our research data management. We use bash scripts or some scripts to build our software, but there are more generalized way to do so, to build software and describe this. And there are also more generalized or nicer ways to execute benchmarks other than just running some run scripts and doing everything by hand. The first category are the so-called package managers, usually or often known by system administrators. They use something like RPM or DEP for providing you software. It's also when you do apt install, then also a package manager has defined the software and deploys it to you. But I want to talk about a user-oriented package manager. And here we have two examples, or I talk about two examples, which are EasyBuild and Spec. Others exist, but I will put the focus here. The idea is to deploy software with these special needs that I told you before, especially in HPC. So you need to build your scientific libraries. You need to manage this very complicated dependency change. Every software built in an environment has to be reproducible on the cluster. So if I do it twice, it should have the same outcome. And it also allows to provide modules for user and facilitates concurrent versions. So when you install something with apt, for example, you have GCC 12, it's not easy to have also GCC 13 and you can use both. You usually update then the one version. But with these package managers, it's really easy to have concurrent software version. This is especially useful for the development or if you're like a performance engineer. So short disclaimer. our software is not built with spec, just the dependencies. But in the future, we will likely include spec and easy build. So this is just my thought, and I will uh, hopefully it will be understandable when I give you like a comparison over these two, and why it is nice to have both of them. So first of all, let's start with the origin. Spec, you could say, is like the US solution, and easy build is like the European solution. The main difference about those two is that spec is very, very flexible. So with spec, you can have things like you just add like text um, to your build to adjust the build. So you can disable Fortran, you can build it with OFast, you can build your framework with GCC 12, but for these targets and everything, so the list can be very, very long. This is really convenient for users and especially for researchers because they can define their needs really spot on. But it's also easy to do errors because there are so many options, and often that's not a good idea to get too extreme with these options. Whereas easy build depends on a hierarchical dependency organization. So you have one dependency chain per easy build config. So every config is a ready-to-use recipe that builds your software. You don't have to do some tags or whatever. It's defined in this easy build config. So it's fewer decisions and it is clearer what to do. This is really convenient if you want to maintain certain versions and especially for server admins. This is also a reason why when you want to really deploy your software as a module, it is more likely that the server or the cluster administrators will add the module for you if you use easy build than you will when you do it with spec. With spec, it's likely that the users define their own environments and build their specs with them. It's also good, okay, but first they have to build it, which can be time consuming. Then spec is completely Python based, so every package is a Python class, and specifications are defined like function calls. So it's like an object. Every dependency or every specification is an option. Whereas with easy build, you have one file, as I said, and the file has different options. For example, the build options and dependencies, and there you have just lists. So it's a really easy overview. I looked into the main repositories of those two and looked as Petsy as an example. And the spec for Petsy was over 800 lines long. These variations, so your build options, they had over 40 of them. Your dependencies probably also have over 40. So when you consider all, you have almost an infinite option of variations with this. Whereas with easy build, you have one easy build file was 46 lines long. For Petsy, you have 3 build options that are either on or off. And in the main repository of easy build, we had 10 easy build configs for Petsy. So it's like it's not too much option there. It's also possible to have like these pre-built binaries, like the public build caches. For easy build, it is something called EESSI, and this is a European solution for this, based on a certain FM. So it's a virtual file system that the cluster has to mount, but I think most of the EU clusters at least do this. So I think for EU projects, this easy might be more important. So we like spec because of the flexibility, but easy because for real integration into systems, it's more likely to achieve with easy build. Um, the last thing are the tool benchmark orchestrations tools. Yeah, benchmark orchestration tools, sorry. Um, I would say I think that they initially were all developed to do acceptance regression tests for HPC systems to see if I have my system, um, does it work? Can I integrate it into my entire network and everything? This is why most of them were developed. Um, but since they are really optimized for these systems, they are also nice to orchestrate benchmarks on HPC systems for own software. So they all have natively integration with workload managers like Slurm. You can abstract um, your build and execution, which makes it more reproducible and more interpretable for users, which is nice. You can span test matrices and or test pools from parameters, which is really helpful to not write or generate like thousands of run scripts. You have just a tool and then you specify all your parameters. They use something, I would say it's called data staging. So the idea is that you divide or that you have the run on a folder and your results for the test in a different folder. So it's yeah, just a data management thing. There is the result collection, and I would say without this, it's hard to get reproducibility, especially in between different teams. The most common tools are Reframe and Jupe. Both are European solutions. There exist also others. But these two at least I tested already, and I think they are the most commonly used also in between for the EU projects, the different COEs. Here I will start with Jupe. Jupe is from the Jülich Supercomputer Center in Germany. You either define XML or YAML configs. I just show YAML. I hate XML. And here you have a very basic Hello World example. So you can see here the YAML definitions. You have these do statements where you then would, instead of echo, run your software. You can also build the software in an own stage. Here you have the definitions of the parameters. They spawn like a matrix, and that can then be inserted here. So you can see here the hello string, and this is how it is called. It is really easy and clean to understand. I think the initial barrier is quite low. Specifically, you probably ran your benchmarks or your software on the cluster before, so you have like a workflow. And this is not forcing you to use a different workflow. It is just giving you an interface to insert your workflow into, which makes it really nice. And especially for the purpose why I looked into them, it was the nicer solution for me. So because we have our build and run scripts, I just want to vary parameter. I don't want to do a lot more. But it's really hard to to model more complex tasks. It's maybe not even intended to do so. And I would say that the scheduler integration is a bit, you have to get used to it. You have to define your batch script, which is okay. And then it's similar to what I showed you before with this Ginger approach. You have macros in your job script, and then you define replacement for the macros that are then also as a parameter be replaced here. Yes, so much about Jupe and sorry. And Reframe is a different flavor. It's from CSCS in Switzerland. And it's Python based, but it has kind of an own DSL, you could say. So it works a lot with these decorators in Python. If you're a good Python programmer, it will be easier for you. But if you are not so used with object-oriented Python programming, you will have quite a hard time. It has really cool, convenient features like when your framework just gives you log files that state like my performance is this in a really long log file, you can regex grab these data and create like data sheets from this with the performance function, which is really nice. Um, it is especially made to handle complex execution graphs, so it's not easy, but it is definitely possible to have complex tasks. And you have simple validation, which is for regression really nice. It's these sanity functions. So if there is something that has always to be true, then you can check it quickly before looking over your results and wondering why it is wrong. It will tell you, okay, the execution was like malfunctioning. It is super strong and flexible. You can basically do everything if you get your Python functionality into it correctly. This power also comes with a lot of pitfalls, so you have to be sure what you do. You can, I would say, easily do errors. Um, these features are really annoying, these convenient features, when you want to model simple tasks, as I wanted to have them, just running scripts. And the initial barrier, I would say, is higher. This is not something that I think anybody can get used to in half a day. So I would spend some time to get used to reframe. But when you are used to reframe, I would say incredible tool. Yeah, and the documentation is one of the nicest documentations that I ever saw. Um, Therefore, plus point for this. Um, Yeah, this I will skip. This is about this interactions for users and to interact via a browser and so. I included a YouTube link here. You can, I think it's not in your slides, but in the uploaded slides, you can check it out. It's a demo where we used one of these, but it's not really a CI tool. Um, this concludes the presentation. It was unfortunately way longer than I expected. Sorry for that. As final words, I would say there are so many tools for all kind of purposes out there. Um, yeah, test them, talk with each other, and there is no tool that is better than the other. You just have to find the right tool for your purpose, but talk to each other to do so. Yeah, thank you for your attention.